Our next molecular mechanics energy term is for torsions or torsion strain, also called dihedral angles. So the energy of a torsion or a dihedral angle will be the sum over all of the torsions in the molecule times a sum from n equals 1 to 6 in principle. Usually there's only a few of them that are included, usually only one, of 1/2 times a parameter Vn, which is the strength of the barrier to rotation, times 1 plus the cosine of n from our sum here, times the dihedral angle or the torsion angle phi, minus a parameter gamma n, the offset or the displacement or offset of that angle. And then summed from n equals 1 to 6, sum over all of torsions. Okay, so what are the parameters and the variables in this case? So we have 4 parameters. We have Vn, which is the n-fold rotation barrier. And that is in the same units of whatever our energy is in here. So that is kcal per mole, typically. We have n, which is just an integer between 1 and 6, as we see. So a lot of times you only have the 3-fold rotational barrier. Sometimes you have things that are 2-fold or 1-fold, 4-fold, etc. But 3 is by far the most common that appears. You have gamma n, which is a phase offset, typically in degrees, could also be in radians. Again, just pay attention to the context of what you're doing there for which is which. And the variable of this function is phi, which would be the dihedral or the torsion angle. Of your system, which again could be either degrees or radians. Just pay attention for which is which. Okay, so we have plotted over here on the right what that example would look like for a typical example in, let's say, ethane. So ethane is a molecule where you can have a torsion. If we look at a Newman projection, where the dot in the center here is the closest carbon atom, and then the circle on the outside is the further carbon atom. So you have HCCH for all of these torsions. There are 9 torsions overall. It's all pairs of H's that are going to the inner triangle and H's from the outer circle. But let's just look at this one particular torsion of interest here. So this would be a torsion angle of positive 60 degrees, being on this side, measuring from this hydrogen to this one. So we have our energy as a function of phi. Phi is restricted in its range to be between 0 and 360 degrees. So let me see that. We can say 0 is less than or equal to phi, which is less than or equal to 360 degrees. Okay, so this is in particular the 3-fold energy of this system. For this case, the only n you have is 3, where Vn isn't 0. So we have our potential starts at 0 degrees up at Vn, and then it goes down at 60 degrees, where it's a minimum, where you have it here, where the molecule is staggered across. Then they're up and they're eclipsed again at 120 degrees, staggered at 180, eclipsed at 240, staggered at 300, and 360 is back around to 0 again. This potential is fully periodic there. Okay, and in this case, gamma 3 for this HCCH torsion is 0 degrees. If gamma were not 0, if gamma were 10 degrees, you would shift this whole potential 10 degrees forward here, or actually, minus, yes. So we'd shift it forward 10 degrees if it was that way, backward 10 degrees if it was minus 10, etc., etc. So as I said, the most common potentials that you see are things that are 3-fold, and then there's also quite a lot that are 1-fold. If you imagine something like butane, so you have the carbon 1, carbon 2, carbon 3, carbon 4. So the CCCC torsion, that would have a one-fold term because it's highest when they're eclipsed, it's lowest when they are fully staggered, and then the actual gauche contributions, those come from a threefold term, which comes from the hydrogens as well. So that would have a threefold and a one-fold term to it. All right, so what are some typical values? What's the typical magnitude of these things that you see? So you'd have V3 for HCCH, the torsion that we're talking about in ethane there, is equal to 1.40 kcal per mole. So notice that these values are much smaller than the typical values we saw in terms of bonds and angles for what their spring constants are. That's because these torsions are much weaker. They're much more able to freely rotate at room temperature, 298 Kelvin. Whereas the bond stretch terms were hundreds of kcal per mole, the bond angle terms were typically around 100 or so. These are at a much smaller order of magnitude, but you still want to keep that preference for staggered rather than eclipse, and that's how you do it through this term here. So we have to specify whatever they are in the system that we have. So as I said, for something like HOOH, something like hydrogen peroxide, there's only one path that we can take. It's just HOOH. That's the only path we got. If we're looking at something like ethane, as I had drawn up there, looking at it from the side, it's got H and the two H's up there. So how many paths are there for that? Well, we can take from each hydrogen, there are 3 paths to each of the other hydrogens. So there's 3 more, and 3 more. So there are 9 total. So we have 1 path in HOOH, 9 paths in C2H6. So that's another caveat to take into account that isn't actually explicitly mentioned here in this potential, but you need to divide actually by the number of equivalent paths that there are. So there's another parameter that's a secret parameter, not really mentioned, but if you actually code this thing, you need to keep in mind is the fact that there is that path dependence of the number of degenerate paths to keep into account there. Because this 1.40 degrees, that's for the entire system there. That's not just for that individual case. Whereas you don't have to worry about that in hydrogen peroxide because it's just the one example. Okay, so this potential energy surface that we're traveling on, that's where we're varying only the torsion angle. So we're keeping all bond lengths and bond angles the same. So that would look something like this if you have a hydrogen peroxide molecule. So I'm going to start there. I'm going to let it go. So notice the OO bond length is the same. All of the OH bond lengths are the same. All of the bond angles stay the same. But it's only actually the torsions which are varying along the side there. So that's the particular energy function that we're traveling along when we see that scan there. Okay, so those are the torsion energy terms. Those are probably the most complicated individual term to actually code up and implement just because there are so many gotchas in that case there. But overall, I'd say in terms of, despite being the most complicated in its actual functional form, doesn't actually take much time overall because there are still a linear number of torsions in a molecule. So you have, for example, if you have a carbon atom, the most number of bonds you can have to that is 4. Nitrogen, the most bonds you can have is 3. The most oxygens you can have is 2. So you're limited in the number of bonds you can have per atom. So since you're limited in the number of bonds you can have per atom, you're limited in the number of angles you can have, and you're limited in the number of torsions you can have. So the number of atoms, or the number of torsions or bond angles or bonds you have in an atom, scales pretty much linearly with the number of atoms. So it's going to be when we get into the non-bonded terms, where it's all atom pairs, that we're going to see really what takes up most of the time in molecular mechanics.